Good afternoon, everybody. This is the breakout on Spring Framework 5.1. It's intentionally named on JDK 8 and 11, but it's not actually as strong a focus as you may seem. So we're not going, as it may seem, we're not going to talk about the JDK all the time. It's mostly a Spring Framework 5.1, what happened at core level update with a strong focus on the things that JDK 8 enabled and how we go about JDK 11 compatibility and what it means to you in the end with a few upgrade considerations towards the end of the talk. There's plenty of chance for questions, so in case you have any, feel free to raise your hand even during the talk. We're going to touch upon several topics, so to some degree it's actually beneficial if you raise the hand during the talk while we all have the context in mind still. Otherwise, of course, questions after the talk are equally fine. All right, just a few words from my personal perspective. Spring Framework 5.1 is an immediate upgrade, of course, from 5.0. It's to some degree the second part of the Spring Framework 5 story. Very literally, Spring Framework 5.0 got released in September last year and was aligned with not only the Java 8 baseline, but in particular with the JDK 9 release. Now, the JDK 9 release brought a general re-architecting of the JDK itself. Many changes, not just the module system. The internal structure in the JDK is totally different. Several API deprecations, quite a few things that don't quite work the way they did before, all of which have been addressed in Spring Framework 5.0 already. So 5.0 is, of course, the start of a new major generation. The way that we handle this in Spring Framework land is that the major generation 4, 5 is quite long-lived. The minor generations like 5.0, 5.1, the feature releases, they supersede each other. So 5.0 is the beginning of the 5 line, 5.1, 5.2 are going to follow. There's a little bit of an overlap in the maintenance window, 3 to 6 months usually, overlap between them, but fundamentally, if you're on 5.0, you're meant to upgrade to 5.1 in the near future and then to 5.2 afterwards. That's how it works on our end, right? We keep the baseline intact, so everything that Spring Framework 5.0 started is still very relevant. Java 8 minimum, Java EE 7 API level, the JUnit 5 support has been upgraded to JUnit 5.3 in the meantime, and in particular the integration with the EE8 API level is still very much a topic in 5.1. There are no news there, simply because nothing has been happening in those APIs in the meantime. So everything on 5.1 is still the same as presented on this slide here as it was in 5.0. Now, in 5.1, we took about a year. It was actually meant to be 9 months initially, but there were several reasons that made us reconsider. So we actually released last Friday, almost 3 months later than planned. But catching JDK 11, right? We've been a few days ahead of JDK 11 GA, which is today. And we were able to upgrade to Kotlin 1.2 in Anger, and in particular to Reactor Californium. Reactor Californium is Reactor Core 3.2 plus Reactor Netty 0.8. Those are important foundational pieces for reactive stacks on Spring Framework for a reactive stack on Spring Framework 5. Spring Framework 5.0 had the Bismuth release train, and 5.1 is based on Reactor Californium. It absolutely requires Californium. We have a very tight integration with Reactor. If you're using reactive architectures to begin with, the Reactor integration is really very much up to the framework itself, a very close companion to Spring Webflux and other facilities in Spring Core. Now, in terms of the feature focus, this is basically just an overview. We do a selection of topics right afterwards, going into more details. But the functional bean definition refinements is very dear to my heart because it's something we started in Spring Framework 5.0. We had quite a bit of uptake, in particular in our immediate vicinity. The Kotlin Beans DSL is based on it. The Spring Kofu project is based on it. We have several research initiatives that strongly go into functional registration instead of annotation-based registration. We'll go into that duality in a bit. And the other really major revision at core level is runtime optimizations, in particular the aforementioned startup time and heap consumption issues, but also GC pressure in the sense of a small, tight Spring application setup, not creating unnecessary GC pressure through temporary objects that need to be cleaned up. The garbage collector may be quite efficient at what it's doing, but nevertheless, it's quite worthwhile to put some pressure off its back, right? So if we can easily avoid initial pressure, then we do this. And this is fine-tuning in the end, but there's a lot of fine-tuning that went into 5.1 all across the framework. In the web application stack, not our main topic in this particular session, but well covered in other sessions at this conference, we also have a couple of themes. Most importantly, the debug log experience. If you run an application on Spring Framework 5.1, turn on debug logging or even trace logging, you'll notice quite different output arrangement. There was previously a bit of a mix of things, of what was happening there. In particular, if you generally enable debug logging for the entire core framework, you got quite a mix in there. In 5.1, it's fine-tuned to a degree where debug logging is kind of friendly to the human eye. And the details are really left to trace logging. So quite a few things have been downgraded from info to debug or from debug to trace. We generally have less log output now at info level and a friendlier log arrangement at debug level. Started for web applications. It was driven by web application logging needs, but it of course went down to the core container, down to core facilities. It went all across the framework. We have a new builder for functional web endpoints, the DSL-style builder, which I'm sure Arjen is covering in his functional fun with the functional web framework session. And there's Webflux HTTP2 support for the Netty runtime. We are already headed for the Tomcat and Jetty runtimes. A bit of a gap that we had to close. We used the opportunity here in 5.1 on React and Netty 0.8 to have HTTP2 support now. So all of these things, of course, shine through to Spring Boot 2.1. Probably not even necessary to mention this, but the Spring Boot release schedule is tightly aligned here. Spring Framework 5.1 is the foundation for Spring Boot 2.1, which just had its milestone 4 late yesterday, and will have a release candidate and hopefully a GA release in October still. So very soon now. So let's go into a couple of deep dives. The JDK 8 foundation in Spring Framework 5 is enormously important to us and hopefully to you as well. It's a little in the details of what we can really do with this, but it's worth elaborating on it. So what does JDK 8 really give us as a foundation here? In all applicable brevity, we already had Java 8 support in Spring Framework 4, right? We still have it in the active Spring Framework 4.3 line. So how does this differ? Well, in Spring Framework 4 and in 4.3 still, we are Java 6 baseline. So the framework itself, everything in the framework is Java 6 and 7 compatible as far as possible. The Java 8 support kicks in at runtime if we detect that Java 8 is underneath our covers here. If we're running on Java 8, we auto-activate Java 8 support. For Java util optional, for streams, for conversion wherever necessary, for Java.time conversion, for everything we technically can do. This is largely reflectively adapting, so we detect your use of Java 8 constructs in application code and naturally understand what an optional, what a completable future, what a Java.time local date is. This is only part of the story. Spring Framework 4 was also strongly about alignment with Java 8 conventions all across the framework, both in terms of API style, callback interfaces, fine-tuned for even more interfaces to be functional interfaces with just one non-default method to declare, and repeatable annotations, etc., etc. We did almost everything that really matters for the application development experience, at least initially. So if you're running a Spring-based application on 4.3, then you'll have a fine experience with Java 8. It will feel almost like a Java 8-based framework to you already. Now, with the adoption, as shown this morning, last year, reaching almost like three quarters for Java 8 already, it was really about time to go beyond this. And this survey is from a month after the Spring Framework 5.0 release, so it quite nicely matches. If 3/4 of people out there are on Java 8 already, we can also do a major Spring Framework generation that is Java 8 baseline, and this is, of course, Spring Framework 5. The entire code base is Java 8 based. Everything, down to every detail. This has been a lot of work because we really mean it. It's not just compilable on 8, right? It's doing things in an idiomatic Java 8 fashion, having the ideal compromise between how we loop, do we do for each, do we do streams. There has been a lot of fine-tuning in this, and a lot of community contributions, I should add here. We've had a lot of pull requests in terms of fine-tuning of the use of Java 8 language, and in particular Java 8 API constructs within the Spring code base internally. There's a few things we can do more efficiently than before, because the reflection APIs had an overhaul in Java 8. We're making good use of this, because there are plenty of places where we need reflection. We can finally expose Java 8 API types now. That is maybe the most important part here. The constraints that we had in Spring Framework 4 were that, of course, the core contracts, the Bean Factory interface, the JDBC template class, all of those core classes couldn't expose Java 8 API constructs because you had to be able to use those exact same interfaces and classes on Java 6 and 7. We could only do Java 8 support in your code, reflectively detecting it. We could not expose Java 8 types directly in our interfaces and classes, because otherwise they wouldn't load on Java 6 and 7 anymore. In Spring Framework 5, we can finally do this. This is the reason why we only did it in 5. Why some things like overloaded methods with Java util function supplies and consumers, overloaded methods that take Java time durations and Java time instance, new methods that take that expose a stream access, Java util stream access. Those only materialized in Spring Framework 5, because this is only possible with a Java 8 baseline. And the other part that I was really looking forward myself there to is the use of default methods. Of course, default methods only work in Java 8 language level or higher, so also require a Java 8 baseline. If you go into the Spring code base right now, many of the interfaces in there, and in 5.1 actually even more interfaces in there, declare default methods. And we use default methods for two different purposes. Default methods have largely been introduced as a backwards compatibility measure, so that you can introduce new methods in interfaces without breaking existing implementations, because the default method has a default implementation against the other interface methods for the new methods. We do this, of course, occasionally, but we actually mostly do it for convenience. We declared plenty of existing methods as default methods, so that for new implementations, you get a default implementation of some less important methods that we can easily default, so that you can focus on what really needs to be implemented by you in case of an SPI interface. That can be quite convenient, and we even turn some interfaces into functional interfaces that way, because a not that well-known fact, actually, in the Java 8 language conventions is that a functional interface, the target of a lambda expression or the target of a method reference in the Java 8 language, is not constrained to just one method. It's constrained to one non-default method. It can have any number of methods as long as all of them are default except one. We're making good use of this. Spring's callback interfaces and in particular in the SPIs. We don't need adapter classes anymore for some things that we used to have. If you were to implement a transaction synchronization or a beam post-processor, a specific beam post-processor type, many of those have default methods now. So a straight implementation of the interface is quite convenient. No need to extend from a base class with stub methods for what you're not interested in. So it really changed our API design. Many of the features in Java 8 had such an influence on how we go about API design and API fine-tuning. Started in Spring Framework 4 already, but it really materializes in 5.0 and 5.1 here. Our duality between the configuration styles, of course, came to a new level in Spring Framework 5. What we call a functional registration, retrieval, configuration style, whatever we're talking about, is really a programmatic on Java 8 style, right? Making the best possible use of Java 8 language and API constructs with basically new API variants that are strongly lambda and method reference based or stream based, allowing you to compose a reasonably complex Spring application setup in a pure programmatic fashion. No use of annotations, if you want to, right? I mean, in the extreme version, there's no use of annotations, no use of reflection, ideally no use of classpath scanning, although you can technically actually do this with custom filters. But none of those things, right? Straight programmatic configuration of a Spring application context, refresh it, and off you go. There's a couple of drivers that we had behind this. It was partly Java 8's functional style, Java util collection streams, and the Java util function package really introducing, suggesting a certain API design style that we're adopting here. But it's also Kotlin. For the Kotlin extensions, which is of course also new in Spring Framework 5, it makes a lot of sense to have a flexible, functionally oriented programmatic API underneath. Our Kotlin extensions all talk to Java APIs eventually, right? The Kotlin extensions basically live in the standard Spring jars. For example, in the Spring context jar, there's a Kotlin extension. If you're using generic application context with Kotlin, it has a few overloaded methods, Kotlin-specific methods with Kotlin API types that you can use. But eventually they call down to Java APIs. So all of the functionality really needs to be in a Java API that can be nicely used, right? Nicely adapted from the Kotlin extensions. And there's the nullability topic, which we'll go into a moment, that partially came with Kotlin as well. So yeah, let's go right into it. The nullability topic is brand new in Spring Framework 5. We didn't really think about it before, I admit, but it's actually a really old topic, right? The Java language does not have a concept for nullable or non-nullable types. Everything can possibly be null anywhere, right? In order for that to be kind of guarded with stronger validations, stronger guarantees to be exposed by APIs that you're designing, you're basically on your own. There are, of course, many measures. You can put notes in the Java doc and assertions at the beginning of the methods. That gets you somewhere, and that's exactly what we did before. But Java doc can be out of sync. Java doc cannot be validated. So there's no help from the IDE for if you're calling an API and can I pass in null here? There's no clear hint that you can get from the IDE. And that's one reason why we considered nullability annotations. The other one is the Kotlin compiler. The Kotlin compiler has, the Kotlin language has the notion of nullable and non-nullable types. And of course, if the Kotlin compiler, from a piece of Kotlin code, if you're calling a Java API, and that piece of Java API does not have any kind of nullable, non-nullable indications in its declaration, the Kotlin compiler has to defensively assume it probably can return null to me for an outgoing return value. So you can't assign it to a non-null type, a non-nullable type in Kotlin, because the Kotlin compiler cannot assume that this is never null. There's a convention in Kotlin They adopted an existing convention that is quite common in some places, nullability annotations. If there are annotations that the Kotlin compiler understands following certain conventions, then the Kotlin compiler will say, okay, this method says it at non-null or non-null by default. It will never return null to me. It says so through an annotation formally. I can make an assumptions about this, and I can allow assignments to non-null declarations in my Kotlin code here. So this is a particularly nice effect, of course. This is not just a validation of the code. This is not just an IDE inspection. This is really enabling a Kotlin language feature through additional metadata in Java APIs. So that was, of course, a driver of its own. The way we do it is that we have largely non-null API and non-null fields by default declarations. If you look at our code and our Java doc, you'll see that there are annotations of that kind on the package declarations. So our package info files have @non-null API, @non-null fields on them. The way that this works is that it's then non-null by default, so strictly parameters and return values that are not otherwise annotated are assumed to be non-null. If they can be null, if you can pass in null to a parameter, or if you can return null out of a method, you declare an @nullable annotation, the exception to the rule. This is the convention that we adopted. You don't have to use defaulting annotations. You could also put @nullable and @non-null everywhere. But this turned out to be the cleaner story for us. Aside from the Kotlin compiler understanding this, we also have some really nice support in, for example, IntelliJ IDEA, where there are several inspections understanding nullability annotations. And IntelliJ IDEA was even updated to naturally understand our specific flavor of annotations, so it works out of the box. If you have IntelliJ IDEA against Spring Framework 5.0 or 5.1, then your code is being validated against the Spring APIs. IDEA will give you a warning if you're trying to pass in null where you shouldn't pass in null. It's also going to help you for return values in particular. Not just that it warns you that you potentially could run into a null pointer exception somewhere, because you could return null here, you could have null returned to you here. It also goes the other way. It tells you about you being too defensive. Like you're making an if this is not null then statement somewhere, and IntelliJ will tell you that's not necessary. You're calling an API that value is guaranteed to be non-null. You don't need to have a defensive if statement there. Both of those things are really valuable. We make strong use of those internally. We use those validations all the time. This allowed us to clean up a lot of code across the code base. I was personally totally surprised how often we got it wrong, in particular overly defensive checks. So a clean nullability story all across the code base was super useful to us. I hope it also exposes some usable effects to you in application code when you're calling our APIs, which are cleanly declaring their null versus non-null rules now. So we actually see some of this even in action on a few slides that follow here. This is actually a fine next example. It's a new feature of its own in Spring Framework 5.1 actually specifically here. The application context does not just have methods like getBean and getBean names for type and getBeans of type now. It has two new methods called getBeanProvider, taking a class or a resolvable type. You can have the same effect if you inject an object provider. So those are meant to be alternatives to each other. You can either declare an injection point like a constructor argument or a field or a method saying object provider of foo, and you get an object provider for this target type. Not a raw instance of the target type, but an object provider for the target type. You can do this programmatically as well, if you're not in the annotation-based model in particular, by taking the application context, saying getBeanProvider for foo.class, and you also have an object provider of foo in your hands. And then you're on the same API. This API is not brand new. It's been introduced in 4.3. And in 4.3, it had already methods like getObject, getIfAvailable, getIfUnique. So you could interact in a smarter fashion. You don't just get the instance or an exception. You get a handle that allows you to lazily retrieve an instance, to retrieve it if it's available, otherwise you get a friendly null value, or to return it if there is a single instance in the context, otherwise return null. All of those have their use cases. So those methods were introduced in 4.3, but in 5.0, we could declare them in a clearer fashion. GetObject itself always returns a non-null value. It will throw an exception otherwise. But getIfAvailable and getIfUnique potentially return null. That's their declaration, right? If it's available, otherwise you get null. So they are now formally declared as @nullable in Spring Framework 5 entire. And what we have down here are also new methods in Spring Framework 5.0. We'll get to the 5.1 editions in a moment. The new methods in 5.0 were largely based on Java util function, like getIfAvailable, but if it's not available, here's a Java util function supplier that knows how to obtain a default instance. That's quite useful, and if you look at the signature, this is not just omitted, it's actually not there. There is no nullable here, because the definition is you get the instance if it's available. If it's not available, you get a non-null instance from the supplier. You always have a non-null instance here. So it's formally not declared as nullable, and we have a non-null by default convention. Same goes for getIfUnique. The other versions with the consumer is also quite nice. If it's available, here's a callback, like a lambda expression. Do something with it if it's available. Otherwise, just skip this lambda expression. So this is already quite a functional API style. You're not obtaining it and trying and catching and checking. You're expressing what you intend to do with it. In 5.1, we have a revision, another revision actually, of object provider here. So it's the same API type. It's got the same methods summarized here again, but there are a couple of new ones. There is support for access to several matching elements, several matching beans typically. So if you have a getBean provider of foo, getObject assumes that there is one or at least a single primary type. There can be several, but you always get the primary one, or you get an exception. GetIfAvailable makes also an assumption of one, or a primary one, or none. GetIfUnique, same thing, right? They all operate against a single match semantically. In 5.1, we have new methods. It's implementing iterable. So object provider is an iterable of its type. So you can even, in a for loop, you can directly iterate over the provider. And it has stream access. You can say object provider stream, give me all the instances, for each do this. Or you can filter the stream, you can turn it into a list or into a set. You can do a registration order stream access, that's the regular stream method. Or you can call you can use what we call an ordered stream. Ordered is the Spring ordered callback interface or the Spring @order annotation. Just like for injected lists and for injected lists and arrays, you can have a stream that is pre-ordered according to the order annotation or the order definition in Spring's ordering model, if that is relevant. There is a difference here in that the iterators and the iterator and the regular stream are lazily resolving. As you iterate, we're going over the matching bean IDs. We are going to retrieve the actual bean instances for you as we iterate. So if you stop iterating, we are not going to resolve further instances to you. This is in particular relevant for lazy singletons, for prototypes, where we are not going to pre-obtain bean instances that you're not even using. Whereas if you're asking for a list of foo, we have to pre-instantiate all of them, even if you might not use all of them. That is also a different, it's a bit of a detail, but worth mentioning. The ordered stream, according to its model, has to pre-resolve all the instances because we can't determine the order unless we have the instance, according to our ordering model. So an ordered stream is actually not lazy, but iterators and regular streams are. So we actually see some use of this here, at least suggested use of it, but this goes into a slightly different territory already, programmatic registration. Generic application context and its subclasses, including annotation config application context, have new register bean methods. They always had register bean definition methods where you build the metadata object and you register that metadata object for a particular bean name. These methods are slightly different. They are designed for a functional registration model. You can register a bean by its class, simply by its class, or in particular by its class, in this case, plus what we call an instance supplier. So these two beans that we register here are basically complete descriptions. Everything's derived from the class. We register the bean foo.class with default conventions. We'll go into that in a moment. And we register the bar.class with an instance supplier. An instance supplier is very specific. We're basically instructing the container that whenever it needs an instance, it's going to call this instance supplier in order to get the instance. It doesn't call any kind of constructor or makes any other assumptions. It just goes straight to the instance supplier. So whenever we need a bar instance, when the container decides that it's time to create the bar instance, in the case of a singleton, that will usually be on startup if it's not lazy init, but it's still up to the container when exactly it will trigger that particular bean, right? There's an order for all singletons on startup. The life cycle is still completely up to the container. And whenever it needs a new instance, we dispatch to this inline lambda expression, which fits the Java util function supplier interface. And it says, well, call the bar constructor. We are calling back to the application context. Give me the primary instance for foo.class, otherwise it'll fail, it's not defensive. And pass it into the bar constructor. So we assume there's a bar constructor that takes a foo. And we're ready, right? There's a foo instance registered up here with default conventions, which means most of the time the default constructor. If there's a single unique constructor, as of 5.1, if there's a single unique constructor, we're also going to call it and resolve its arguments. And if you build a Kotlin class and there's a primary Kotlin constructor declared in that class, we're going to use that. If there's no default constructor, that is the only thing we can do anyway. The default constructor is always a fallback. So there is a set of conventions applied to how to create the class if there's no instance supplier. This example below is a bit more specific. It's illustrating a few things you can additionally do. The foo class variant here has an instance supplier. This is actually an instance supplier. It's a Java 8 method reference, also matching the Java util function supplier interface. It's a direct dispatch to the default constructor on foo. Doesn't look that exciting, right? But there is a difference here. There's a set of default conventions up here that we're checking. And if we're finding such a constructor, we have to reflectively invoke it. There is no reflection down here. If you're passing a method reference to a particular constructor in here, there's no guessing on our end. We are going to straightforwardly dispatch to what you gave us here, to this default constructor on foo. It's an invoke dynamic instruction in your bytecode. There's literally no reflection. The bar registration is also slightly spiced up here. There's a slightly different bar constructor call, a constructor of bar that takes an object provider of foo. Maybe it lazily accesses foo. That's the most common case for using an object provider. Maybe it has to make some availability uniqueness checks. Maybe there could be several instances of foo and it wants to stream over them. All of those are good reasons why you want an object provider. That's exactly what we are obtaining here and passing into the bar constructor. Just like if it had add auto-wired and an argument object provider of foo. And there's actually another lambda expression down here. This lambda expression says bean definition lazy init. It's what we call a bean definition customizer. There can be any number of those. So what we do here is that we register a bean, derive some conventions from the class. So we take the instance supplier if you give it to us. And before we register the bean definition, this metadata object underneath, we give it to you as a callback. Here's the bean definition. with the bin definition interface, please apply any further metadata. Add some attributes, set lazy init, set primary, add a qualifier, do whatever you need to do. And it's just an inline expression. If there are several things to set, several inline expressions separated by a comma. So this is what I mean with making the best possible use of Java 8 language features in core Spring facilities, both for the retrieval of other beans and in particular for the registration of other beans. Not the main topic in this session. There's a dedicated Kotlin talk by Sebastian Deleuze that I highly recommend, I believe on Thursday. It's programmatic bean registration with Kotlin makes use of Kotlin extensions. And just to give you an idea of what this means, there's kind of a variant of this example. There are two variants of this example to be seen here. This is Kotlin code. Almost looks like the Java code before in the version above here, but it's actually calling Kotlin extensions because Kotlin, what we produce here is a Kotlin K class, and this looks a little like a Lambda expression, but it's really a Kotlin function. And there are overloaded methods for those particular types so that you don't have to adapt anything. Semantically, it's very similar, registering it with default conventions for calling a constructor. And here we are registering it with an instance supplier. If you look carefully, you'll notice that there's no extra argument. Didn't we say bar.class plus instance supplier here? And here there's basically just an instance supplier. This has a technical reason. Kotlin functions retain their return type. Lambda expressions in standard Java and method references in standard Java, unfortunately, do not return their return type. So if we receive a Lambda expression or a method reference in Java, we do not know what it will return to us. There's no reliable way of inferring the return type. So there's an extra argument. We're saying, as a caller, basically, you have to say, this is what I'm producing, and this is the little Lambda expression that actually produces it. In Kotlin, we can reliably infer that this Kotlin function returns an instance of type bar, so there's no need to repeat yourself. This is one example where the Kotlin extensions just allow for a smoother usage model if you're within Kotlin. What you can see down here, what I'm dubbing the Gradle style usage of the Kotlin extensions, uses the exact same methods with a slightly different variant of the Kotlin language. Nested register bean calls on the outer type, and it uses Kotlin generics, which is kind of a nice flavor here. It's basically equivalent to the call above, but it's not specifying a K class. It's using generics, but the generic argument type is going to be passed into the method call by Kotlin conventions. So that's quite nice, I'm calling it Gradle style because it sort of feels a little similar to the Gradle Kotlin DSL. The Gradle build tool has a Kotlin DSL as well. This is still pretty basic usage of Kotlin here. We have a fancier declarative bean definition DSL in Kotlin as well that Sebastian certainly is showing at this conference. So there's several flavors in Kotlin. Of building a Spring application context. The storyline is basically the same. We're making the best possible use, idiomatic use, of Kotlin language features in interaction with Spring Framework APIs. Basically the same story as with Java 8, just applied to Kotlin through the Kotlin extension model. And the Kotlin extension model is actually a really sweet enabler. So kudos to Kotlin, to the Kotlin team. They really went to some extra lengths to have a flexible extension model that does not creep into the Java classes. Generic application context is the same generic application context as you know from Java, but there's a little generic application context extensions.kt file in the Spring context jar. The Java compiler has no idea that this file is relevant, but the Kotlin compiler by convention says there's a Java type, there's an extension type in Kotlin, it kind of merges the views and adds the extension methods to the base Java type. You can see the unified type from the Kotlin compiler's perspective. It's a great model. It allows us to ship Kotlin extensions in our standard Spring Framework jars, the same jars that you get from Maven Central, the exact same version. They do not mess up the Java experience at all, and they magically make the Kotlin experience richer than before. It's a really nice model that we're making good use of here. Another example of what we can do here, and just a quick note really on it, since it's primarily used in the web layer, is data class binding. In Spring Framework 5.0 and significantly refined in 5.1, we have a flexible binding model. Data binding in Spring MVC and in other places in Spring is primarily known as being property setters, right? We instantiate the object, we pass in the incoming parameters or arguments through individual setter methods and populate the object that way. We are a little bit smarter now. If we detect that an object does not have a default constructor, if it's not a regular Java bean, we automatically switch into a different mode of binding. Because we know that it's a binding target. You gave it to us. You declared it as a binding target. So instead of failing and rejecting it, we're saying, OK, let's look at the constructor. Is there a primary constructor? There's a definition for this in Kotlin and a similar convention for Java. Usually it means a single constructor. Not necessarily, though. In Kotlin, it's a little smarter than that. We look at the signature of that constructor, infer the parameter names, and inject the corresponding parameter values from the incoming binding source. So just like we would call setName and setAge on a Java bean, we extract the name and the age parameter value and convert those, pre-convert them, and pass them into the constructor. This can be used for Java binding targets. You can implement Java classes with the same conventions, but it's particularly nice for the Kotlin data class model and for Lombok data classes, both of which have very similar conventions, basically follow the same conventions we are adopting here. So this line above here is a complete Kotlin data class, including accessors equals hashcode toString. And this is the Lombok equivalent, slightly different programming model because the outcome is basically the same. Kotlin is driven by the constructor and infers the fields and the accessors from it. In Lombok, it's driven by the fields, and it generates the constructor and the accessors from the fields, right? But the outcome is basically the same, the class that results from this, and we can bind to it the same way. So it's also a little bit Kotlin-oriented, but it works fine with Lombok, and you can match the same conventions in plain Java as well, and it kind of goes nicely with other efforts that we have in Spring Framework 5. All right, let's move on to the JDK 9 topic. JDK 9, 10, 11 topic, right? If you're saying 9, I was saying so last year already, if you're saying 9, you're really saying 10 and 11 in the same sentence, right? 9 was designed as a short-lived release. It was only really active for half a year. It's already end of life. 10 was its immediate successor in March this year, and came with some really nice stuff on its own, but again short-lived, non-LTS, and it's actually end of life as of today, right? JDK 11 released today is the first long-term support release that is really kind of an accumulation of everything that happened since JDK 8. So all the goodness we got in JDK 9 is in there. The few little refinements like the var statement in JDK 10 is in there. And we have a few nice little API additions as well. So this is basically JDK 11 now as a major upgrade with long-term support that we can really care for. JDK 11 is just like JDK 9 based on a module system internally. And it's actually a little different from 9 since 9 deprecated several modules that used to be in the JDK and 11 removed them. There is no JXB in JDK 11 anymore. There is no common annotations, JavaX.annotations, in 11 anymore. No JXWS. They basically dropped a lot of stuff from JDK 11. Historically speaking, those all have been additions in Java 6 at the time when Sun decided that all of this needs to be in the JDK because .NET has it as well in the core distribution. So, and now they are kind of undoing it. And the contents of the JDK are a little more on the pure end now, not containing any kind of higher level or web-oriented facilities anymore. A little bit like JDK 5 and earlier were. So that's JDK 11. in terms of its setup, it of course comes with the goodness that they introduced in 9, like the JLink tool, building custom JVM distributions based on the module system, selecting modules by name that need to be in there, and only those modules are going to be accumulated into a sort of bytecode image that you're then distributing. It's actually not particularly fancy what they do in JLink, but it's still nice. Unfortunately, it only works with fully declared modules and a fully declared module dependency graph, which is quite a limitation, as we're going to see. From an API designer's perspective, a library perspective, a framework perspective, JDK 11 is quite a different beast from 8. We have to make very careful assumptions about what we can rely on in a particular JVM. Not only the Jigsaw and common annotations and co being removed, there are also several modules that are optional now, like JNDI or even Java util logging are not guaranteed to be present. In a standard JVM setup, you have java.base active and everything else you have to opt in. You have to enable those modules at runtime. And in a custom JLink image, they might not even be there. So it's kind of interesting, right? We all, over the years, learned that lots of things are present in the JDK by default. They are simply there, always there. That's not quite the case anymore in 11. And in a custom JLink image, the only thing that is guaranteed to be there is java.base. So this is the original Jigsaw module graph from pre-11 still, where they had quite a few of extra modules that in the meantime got removed. But this is what they basically decomposed the JDK into originally. You can see that there are a lot of additional modules. Java.base is at the bottom. Everything else is essentially optional from a modern day perspective. So if you design reusable code, you shouldn't really rely on the presence of JNDI or even the XML libraries or Java util logging because they are all optional modules. Even JDBC is an optional module in JDK 9 and higher now. So this is quite a different world. From a Spring perspective, it's not that different because we always targeted Google App Engine and other special JVM environments where some of those modules were not included in other JVMs before. So we already had defensive assumptions about the presence of, for example, JNDI or Java util logging before. And this is really a good fit with where the JVM is going here. We didn't have to redo many things in Spring. The problems are mostly in other libraries. Hibernate, for example, really relies on the presence of JNDI and Jigsaw. It really needs them at the moment. Even on going forward, they will still need it, but they will deliver POMs that bring them in from Maven Central. Because everything that is not in JDK 11 anymore, in particular like pieces like Jigsaw, you have to get the reference implementations from Maven Central now, if they are not in the JDK anymore. You can keep using those APIs, you just have to get them yourself. Now, this is JVM distributions, right? You can build custom distributions with JLink, and it's the internal structure of the JDK is modularized. On top of that, you can choose to use the module system. I am still using its original code name Jigsaw here. It's officially called the Java Platform Module System now. You can choose to use the module system at the application level. This is now basically about how you deploy your code onto a JVM 11. The class path, of course, keeps existing. So the simplest way is simply to take your chars as you always did and start the virtual machine with java-cp, register your stuff on the class path, or drop them wherever you dropped them before into a web-in-flip directory, start up Tomcat the same way as before. That keeps working. But beyond that, you can choose to explicitly design, to handcraft, a module-oriented layout for your application, for standalone applications in particular. You can choose to take your jar files, add module descriptors to them, and deploy them to the so-called module path on the JVM. The module path and the class path are really almost two modes of operation, two modes of deployment on the JVM. The class path is still quite lenient. There may be overlaps between the jar files, etc. You may call non-exported APIs, you just get a warning. Whereas on the module path, no overlaps. It's going to fail if a package exists in 2 jars. If you call a non-exported API, immediate failure. The module path is much, much stricter. A module technically is literally just a jar file with a module descriptor, either a full module descriptor or a module name manifest entry. This is what they call what is being called an automatic module. It's basically just a manifest entry. In the jar manifest, it says automatic module name, refer to me by this name in the module system. Default conventions for everything else. Gets you quite far, but it's not quite the full story. The full story is a module info descriptor along those lines, basically saying, okay, declaring my jar file as module with this name. It requires this other module and that other module by name, and it exports certain packages to other modules. Not everything, just those packages. Everything else is internal to my module, not to be accessed by other modules. This is essentially a module descriptor. There's a little bit of fanciness beyond that, but fundamentally that's it. From a Spring perspective, Spring's modules as of 5 have automatic module name declarations, so you can refer to them with a well-defined module namespace. So requires Spring.jdbc literally requires what's deployed as Spring JDBC jar. Those conventions are pretty straightforward and kind of match the names that we use for the artifacts intentionally in our case. We don't ship full module descriptors yet. We get to that in a moment. But we allow for consumption of the Spring Framework jars in a module setup that you are handcrafting for your applications. And a couple of other, quite a few actually, other open source projects do exactly the same thing. They declare automatic module name headers, but no full module info descriptors quite yet. Automatic modules, in the case of Spring, get us quite far because we're seeing other modules that are deployed. We can optionally access other modules like Jackson or Hibernate as they're being deployed, but we cannot pre-declare references to their names yet, so we don't actually declare that reference. It's kind of implicitly arranged at runtime for us. That's quite nice because we do not have to bake names of external modules into our descriptors. This is actually the main feature, or the main reason why we use automatic module names, the main feature of automatic modules. We'll get back to that, summarizing it in a moment. Now, another common topic, right, common question. Reflection into module-contained classes. We have fortunately, an arrangement here at JVM level that is quite friendly towards assumption that Spring typically makes. The simple version of the story is, as long as you declare everything as public that Spring needs to access, like Spring calling public constructors, public setter methods, public request mapping handler methods, as long as those artifacts are public that you expose to Spring, you're fine. You don't need to do anything extra. However, if you want Spring to see internals, if you want Spring to inject non-public fields or to call non-public constructors, then you have to open the entire module or at least certain packages in your module to us. So in the Java platform module system, there's a concept for opening a package. You can export the package or you can open it. Exporting basically just makes it visible, but primarily the public types, that's what it's really about. And only if you additionally open the module, declare it as open, or if you at least declare certain packages of yours as open, then you allow for deep reflection, for reflection to non-public, for the invocation of non-public methods and reflection into non-public fields, etc. So a simple version is you don't have to do this. Our design recommendations are exactly that you should use public constructors and public handler methods because that makes your components testable, not just accessible by the framework. So if you follow typical Spring conventions, you're good. Just if you have an arrangement where non-public artifacts need to be referable from Spring, don't forget to declare your modules as open, or at least the affected packages as open. So back to the limitations. In our current arrangement, the Spring jars are automatic modules. They have well-defined module names. Dependencies automatically resolved at runtime for us. That's actually quite nice in practice. And it's the same arrangement as for other open source libraries, so we are certainly not the only ones doing this. This is basically the state of the art right now. It gets you pretty far. It makes those framework jars referable in your application modules by name. Pretty much everything you would typically do works fine, except for JLink. The JLink tool for building custom JVM distributions basically doesn't accept automatic modules. Everything you're trying to include in a JLink module arrangement needs to have a module info descriptor and fully declare its dependency graph. We are simply unable to do this in Spring at the moment. Practically unable because some of the modules that we refer to, of the other open source libraries that we optionally integrate with, do not have stable module names yet. They don't declare module names, so we don't really have a proper name to refer to them in our module descriptors, which is a shame because a module descriptor is a binary artifact. If we are shipping this, there has to be a well-defined name in there. Otherwise, if the name for any reason changes, the default name is derived from the jar file. So if you rename the jar file, the name has changed, then we have a problem, right? And there are many optional modules in Spring. The Hibernate support, Hibernate Validate, Eclipse Link, Jackson Databind, Jackson itself, Google JSON, all of those are optional dependencies. So all of those have to have well-defined module names before we can ship full module descriptors that are usable with JLink. At this point, I cannot see this happening before like 2020. It's basically Spring 6 timeframe. It's unlikely to happen in the Spring Framework 5.x release. Also for the reason that we need to build on JDK 11 or higher for that to really work, because the module descriptors are only really, the language of the module descriptors is only really active in the Java 9 source level or higher. So if you want to compile with Java 8 compatibility, we have a problem. We have to do split compilation and other unfriendly things. So it's simply not feasible, and we don't see enough reason to do it at the moment. There's also another little twist. What JLink does is nice, but actually doesn't have that many benefits unless you really care for disk space or distribution size. That may be a reason. What's currently happening in GraalVM and all the options that GraalVM has for native images on its so-called substrate VM is much, much more compelling. This at least potentially has enormous benefits for startup time, for memory consumption, and not just for the image size, not just for the disk space. And I can see by next year, I can see GraalVM to become really compelling once it's final for a start, and hopefully align some conventions a little bit further. Then I can see this being a quite compelling choice where JLink possibly isn't that important as a tool anymore in a typical Spring application context. But in any case, once we go Java 11 plus, so once there will be a Spring Framework generation that requires Java 11 as a minimum, by that time, 2 or 3 years at most, we will certainly require, we'll certainly ship module info descriptors and just make assumptions about the optional modules that are left by then. So it is a temporary problem, but the temporary phase will still last for at least 2 years. A couple of further considerations. We have a quite strong recommendation for the class path. I don't really want to kind of oversell the module system. It's nice on its own, right? It's worth discussing, it's worth considering. And at the same time, I feel that the module system brings some really long desired benefits, right? I'm quite torn personally on the module system. The class path is an unstructured sequence of zip files, basically, and directories. And we force the JVM runtime to kind of search those in the order of declaration. That's quite inefficient and quite old school these days, right? The module system is a stricter formal deployment arrangement with validation at compilation time, validation at startup time. It detects many deployment mistakes, right? Like overlapping jar files and so forth, right? So there's a much stronger set of guarantees attached to a deployment with the module system. That's all nice. However, it's also quite constraining. Not necessarily from a Spring perspective. So if you choose to use the module system for application modules that run on Spring 5 or higher, you'll have a fine experience so far. If you're on JDK 11, please don't forget to use Spring Framework 5.1 or higher. Spring Framework 5.0 on the JDK 11 module path is going to fail if it tries to define custom classes. Use Spring Framework 5.1 if you're going to JDK 11 or higher, in particular on the module path. So yeah, both of the options are available, but I would consider the class path as the default. And in some cases, you can't even argue about it because it's not in your hands. If you're deploying to Tomcat, you're deploying a WAR file with a nested class loader arrangement and the web in flip directory, you're not directly touching the class path or the module path, so it's simply not your choice to begin with. If you're using Spring Boot, you'll typically just let Spring Boot and Spring Boot's dependency management assemble your class path, and you don't really manually care for it. So in that sense, it's simply not that big a deal, and there's a degree of validation of your deployment layout that tools can provide to you as well on deployment. It doesn't have to be the JVM, right? Overlapping jar files, etc. You can detect this in other ways. You don't necessarily need the JVM to validate this on startup. So in that sense, the value proposition in the module system is not as significant, right? As it's basically nice and good to have, and certainly progress from where we were with the class path. It's just not that strong a driver, right? It's not a hard argument. It's like, oh, I can only accomplish this when using the module system. There's hardly an argument in that direction. It's more like, I can use the module system for this, and it's kind of nice and cleaner and stricter. Yeah, well, it's more formal. There may be good reasons why you're choosing it, but they're basically all soft reasons, not hard reasons. I haven't explicitly mentioned this yet, but if you're deploying to the module path, there's no difference in the class loaders. You still get a unified class loader for your entire deployment layout. This is not OSGI, not a class loader per bundle model. It's still one large class loader for your entire module arrangement. So your application basically can live under the same class loader assumptions as on the class path. That's kind of nice from a backwards compatibility perspective and for frameworks and libraries running on it, but it once again means there's no real difference, right? It's also not a reason where the module system has a significantly better runtime arrangement behind it. So in that sense, consider staying on the JVM class path, in particular initially, and in particular if you're using other libraries and frameworks. If you're using Netty, if you're using Hibernate, even Jackson, well, I mean, it's kind of okay-ish if you use them on the module path in the meantime, but you're up for a certain degree of initial trouble that you have to sort out, whereas on the class path it simply keeps working as it did before. So you'll have a smooth experience when you're upgrading on the class path for a start. The upgrade to JDK 11 also bears the question of which bytecode level are you using for compilation. Just because target 11 is the default for the Java compiler on JDK 11 doesn't mean you have to use it, right? You can upgrade to Java 11 and keep compiling with target 1.8 or with target 9 or with target 10. All of which increase your chances of other libraries and tools working properly. Because the single biggest nuisance in the new JDK release model is that there's a new bytecode level, a formal bytecode version every half year. So every tool out there and every bytecode generation library out there needs to understand that new bytecode level. There may not be many differences, but it's technically a new version, and in Java 11 there are actually significant differences in there from 10. So if you're using a slightly older library, a slightly older tool, slightly older check style version, or build tool, or an older Groovy version, or an older version of Spring, they might not understand that new bytecode level. An easy way out, at least for a transition phase, is to keep compiling against an older level. Keep compiling your existing Java 8-based application with target 1.8, but deploy it to JVM 11. That is on the class path. That is the single easiest arrangement that you can choose. Many, many applications with up-to-date dependencies in them are simply going to run fine that way. So for an existing, say, Spring Boot to the .1-based application that works fine for you on Java 8, take the exact same app, run it on a JVM 11, with no differences, keep compiling on target 1.8, keep deploying to the class path. Chances are it'll just work fine. And you'll have a very smooth upgrade experience. The next step, of course, could be, oh, I want to use new language features. I want to use the var statement from JDK 10. Well, that might be a reason why you increase your source level and your target bytecode level. But that can be a subsequent step, and it can happen at a later point of time. Spring Framework 5.1, I should add here, is of course as up-to-date as can be. It actually ships with an ASM 7.0 fork that fully understands the Java 11 bytecode level already, and is already prepared for the Java 12 bytecode level. But that's of course only covering Spring's concerns, right? If you're using Hibernate, or if you're using Groovy, if you're using Kotlin, you'll have to live with the versions of ASM or other bytecode libraries that they chose to use and chose to embed. Right, in that sense, you could even build against JDK 11 and run on JDK, build against JDK 8 and run on JDK 11. You could also build against JDK 11 with target 1.8 and run against JDK 11 if you feel better about it. All right, that's really all I had for today. So just summarizing that many of these things have been started in 5.0 last September. 5.0 is compatible with JDK 9 and 10. It didn't receive the JDK 11 updates. Those are really in 5.1 because they are quite significant. As I mentioned, most important takeaway, if you want to have a good, smooth first experience on JDK 11, please upgrade to Spring Framework 5.1 at the same time or before. It comes with full support for JDK 11. It comes with initial compatibility with GraalVM if you're willing to experiment with this. Ironically, GraalVM only really works on Java 8 at the moment, but that's a separate topic. We ship with everything as up-to-date as possible, ASM 7, reactive Californium. There's support for Hibernate ORM 5.3 in there, which I haven't really mentioned before, but it's actually quite nice on its own. We have bean container integration with Hibernate, so all of the Hibernate managed callback types in JPA are now injectable through Spring out of the box, or can be injectable out of the box if you choose to do so. That's a quite nice arrangement. There's a significant overhaul in our Hibernate support in general, also for mixed JPA and Hibernate access in the same transactions. So if you're a deep Hibernate user, check out what we did in Spring Framework 5.1. I hope you like what you'll see there, in particular when you intend to upgrade to Hibernate 5.3. All right, and our next step is Spring Framework 5.2, as mentioned this morning. We have a backlog. If you want to see what we have in the backlog on Jira, 5.x backlog, that's the candidate list for 5.2, basically. There's a few things we'll definitely do. Support for JDK 12. We'll complete our GraalVM efforts. We'll catch up with Kotlin 1.3 with the coroutine model, ideally. There's a few things lining up for Hibernate 5.4. Looks like that will happen in time for our release. We have a few things that we are considering in the reactive space, a reactive transaction model, where some of those things will happen at core framework level and then be leveraged in higher levels, at a higher level in Spring Data and in Spring Boot. So there's quite a bit of there's always quite a bit of work left, right? But in this case, we have actually a quite concrete set of items that we intend to wrap up towards June 2019, release candidate in May, and the GA in June. In all likelihood, Spring Data and other Spring projects are going to follow that release train, so you'll also get major releases of other Spring projects in the same time frame. So thanks for your attention. If there are any questions around any of this, anything I can possibly help you with, I'm of course available. If you want to raise a question in the auditorium, there's one quick chance right now to do this, maybe. Otherwise, just come up to the stage afterwards, whatever you prefer. Any question for the auditorium? Sure. So the question is the framework opinionated in any way about programmatic registration versus functional style registration versus annotation-based registration? We're trying not to. So don't get me wrong, right? The annotation-based programming model remains as kind of a first-class citizen, as the mainstream programming model in the Spring ecosystem, for sure. Right? There's no doubt about this, and we're not questioning or challenging this. The functional registration model basically sits there as an alternative. It is an enabler for quite a few things. If you want to see what we're doing with this, there's the Spring Foo project with Spring Kofu and Spring Jafu as a kind of reference projects for a DSL experience with Java or Kotlin against this. So this is only the beginning of kind of a line that we are further exploring. And it's really meant for smaller scale setups, right? If you're registering, say, a dozen components or so that may even fit on the screen, right, on a single screen. So it's a little related towards microservices for all these minimal deployment in constrained environment efforts that we have. Functional registration is a great companion, right? A very small, tight deployment unit that you can then easily ship, and it starts up very quickly. Function as a service models, they all have requirements that go in this direction. And you can mix and match. This is actually a very much a Spring theme over the years. We are never doing like this model versus that model, and they're just separate islands. You can mix and match all the way through. You can register beans in the functional model, but those beans can have at transaction annotations and at auto-while injection points in them. This mixes and matches very, very nicely. We pay careful attention that we leave room for shades of gray, right, in between. In that sense, we're really not very opinionated about it. We're really trying to enable slightly different usage models to the degree that makes sense for your purposes. Personally, I'm quite happy with the way this worked out in 5.0 and 5.1, and with everything it enabled, in particular on the Kotlin end. So there's also, if I may rephrase the question just towards like, is there a kind of opinionated, an opinion here, if you chose to use Kotlin already, maybe, right? With Kotlin, the functional registration variant is really a little bit nicer as with Java still, and a little bit compelling. But at the same time, the annotation-based model works just as fine with Kotlin, right? So it's maybe a little bit of a tendency towards programmatic registration if you chose to use Kotlin beforehand, but not a strong argument either. All right. Yeah, sure. One more I'm happy to take. That's what? Oh, the nullable annotations, yeah? Optional. Good question. So why we're not using Java util optional instead of the nullable declarations that we have? Well, Java util optional really influences the API signature that the Java compiler sees and the JVM sees, right? So for existing APIs, you have kind of to overload the signatures or even break the signatures in some cases, whereas the nullable annotations allow us to redeclare existing signatures. The signatures remain binary compatible. They're just a little bit stricter in their definition, but existing code keeps working, precompiled code keeps working. It's a very, very nice transition. That's for one, right? And the other one is that Java util optional is a little bit unwieldy. It's like extra, it's a little bit of extra ceremony around them. We saw in Kotlin, or we got inspired by Kotlin, where this is really not Java util optional like. It's like a formal nullability characteristic for a type declaration. We really like this, and we try to stay as close to it as possible. And nullable declarations in Java are the closest you can get to the signature style in Kotlin, right? This really matches very, very nicely. It's a direct match, whereas with Java util optional, we'd have to adapt for every single case. So there are several reasons, but I personally believe that Java should have a language level nullable indication. Java util optional is nice for stream APIs. It's nice for certain API styles. It's not a general purpose answer to the nullability problem, in particular for incoming parameters. So that's why, right? There's a bit of a longer reasoning behind this, but it has been considered. And we even, if you look to Spring Framework 5.0 milestones, there are earlier milestones in Spring Framework 5.0 that had a few APIs with Java util optional. We backed this out again in favor of nullable, right? We tried it. We didn't like the outcome. So we went with nullable in the end. All right, so we'll have to wrap up. If there are any remaining questions, I'm here. Please just come up to the stage or catch me anywhere.